Okay, we're going to go ahead and start the last lesson in Chapter 9, which deals with models for population growth. Today we're going to look at exponential growth and decay and half-life. And then to wrap this lesson up, we'll take a look at logistic growth later on. Okay, so as far as exponential growth and decay goes, we are going to let y be a quantity that increases or decreases at a rate proportional to the amount present, which means we can write that as a differential equation. Dy dt is equal to k times y, where k is a constant. And we are also given the amount of the quantity or population at time t is equal to 0 is y sub 0 or y naught. So that means that the amount or population at time 0, y of 0, is equal to y naught, y sub 0. And this is going to be a separable differential equation. Okay, so let's go ahead and work through the solution to the separable differential equation. And to do that, we're going to do integration by separation variables that we went over in section 9-3. Okay, so for us to do that, we're going to go ahead and divide both sides by y and multiply both sides by dt. So we get 1 over y dy is equal to k dt. And then we have that initial condition as well, which is going to allow us to be able to solve for our constant. Okay, so when we go ahead and integrate both sides of this equation, we get the natural log of the absolute value of y is equal to the integral of the right-hand side is kt plus c. And then we are going to want to isolate y. Okay, so to do that, I'm going to apply e to both sides. And when I do so, the e and natural log on the left-hand side cancel. So that just leaves me with the absolute value of y is equal to e raised to the kt plus c power on the right-hand side. And then because I'm adding exponents on the right-hand side of the equation, I can rewrite the right-hand side as e to the c power times e to the kt power. And then I'm going to go ahead and drop the absolute value bars on the left-hand side by putting a plus or minus in front of my expression on the right-hand side. And then I'm going to rename the constant plus or minus e raised to the c power out front. I'm going to go ahead and call that a. So y is going to be equal to a times e raised to the kt power, where a is equal to plus or minus e raised to the c power. Okay, so once I have that, I'm going to go ahead and use my initial condition where y of 0 is equal to y sub 0, and that's going to be equal to a times e raised to the k times 0 power. So that's going to make e to the 0 power, which is 1, so that makes y naught equal to a, which makes my function then y of t equal to y sub 0 times e raised to the kt power. Okay, and this right here is our formula for exponential growth or decay. Okay, so that is the formula for exponential growth or decay. All right, and that is the real calculus involved in this section or in this lesson is the derivation of the exponential growth or decay formula. Okay, so let's just summarize what we talked about. So our law of exponential change states if y changes at a rate proportional to the amount present. Okay, so that means the rate of change of the population with respect to time is equal to k times y. So some constant k times our population y. And y at time 0 is equal to y sub 0. Then our function y of t will be y sub 0 times e raised to the kt power, where if our constant k is greater than 0, that represents exponential growth. And if our constant k is less than 0, that represents exponential decay. All right, and the number k is called the rate constant. So if k is positive, we typically call it a growth constant. And if k is negative, we call it a decay constant. Okay, so let's do a few examples illustrating this law of exponential change. All right, so the first one, directions ask us to find the solution to the differential equation dy dt is equal to k times y that satisfies the given conditions. Okay, so again, we have a separable differential equation, dy dt is equal to k times y. We are told that the initial population is 50 and the population at time 15 is 30. So hopefully looking at that, you can tell that you're looking at an exponential decay function because as time elapses, the population is getting smaller. Okay, so let's just work through one more time just to make sure we're all clear with the process of deriving, in this particular case, our exponential decay function. Okay, so again, if we use integration by separation of variables, we get 1 over y dy is equal to k dt. When we integrate both sides, we get the natural log of the absolute value of y equal to kt plus c. We apply e to both sides, so that's going to make the absolute value of y equal to e raised to the kt plus c power. And then I'm going to rewrite the right-hand side as e to the c power times e to the kt power. Okay, I'm going to drop the absolute value bars by putting a plus or minus in front of the expression on the right-hand side. And then I'm going to rename that constant plus or minus e to the c power as a. So that's a times e raised to the kt power, where a is plus or minus e raised to the c power. Okay, so once I have that, I'm going to use my two initial conditions to figure out the value of a and the value of k in this formula. Okay, so I can use the first initial condition where y of 0 is equal to 50. So y of 0, that's equal to 50, which is a times e raised to the k times 0 power, which makes a equal to 50. Okay, so I'm going to go back over here and write it up a little bit higher. So that's going to make y of t then equal to 50 times e raised to the kt power. And then I'm going to use my second initial condition to figure out the value of k. Okay, so we know y of 15 is 30. And that's equal to 50 times e raised to the k times, we're going to replace t with 15. And then we're just going to go ahead and solve this equation here for k. Okay, so I can go ahead and isolate the exponential on the right-hand side, dividing both sides by 50. So 30 divided by 50 simplifies to 3/5. And that's equal to e raised to the 15k power. And then I'm going to apply the natural log to both sides. So we get the natural log of 3/5 equal to the natural log of the right-hand side just becomes 15k, which makes k equal to the natural log of 3/5 divided by 15. Okay, so that's going to make my function y of t then be 50 times e raised to the power of the natural log of 3/5 divided by 15 times t power, and that's my function. Now, at first glance, it doesn't look like our k value is negative, and we said because this is an exponential decay function, k's value should be negative, but this value for k here is in fact negative, because if you think about the natural log expression, the natural log of 3/5, the natural log function graphically looks like this, where it has an x-intercept at the point 1, 0. So any value between 0 and 1, the natural log of that argument is going to be negative. So while k doesn't look negative, k is in fact a negative quantity like we said it would be, and that is our exponential decay function in this case. Okay, let's move on to another type of exponential decay function, a half-life problem. So directions here say that the half-life of radium-226 is 1,590 years. You guys have all taken chemistry, so you know what half-life is. Half-life is the amount of time it takes for a radioactive substance to reduce to half of its starting mass. Okay, so the half-life of radium-226 is 1,590 years. Part A says a sample of radium-226 has a mass of 100 milligrams. And then we're asked to find a formula for the mass that remains after T years. In part B, it says find the mass after 1,000 years to the nearest milligram. And in part C, when will their mass be reduced to 30 milligrams? Okay, so let's go ahead and work this one out. With these half-life problems, if you are not told what k's value is, that is always going to be your first step. Okay, so you want to figure out what the decay constant is going to be. We're not explicitly told what k is here, so that's going to be our first step in this problem. So let's go ahead and do that first before we figure out what k is, or before we do part A. Okay, so we know our starting mass is 100. So we're going to go ahead and plug that. Well, let's go ahead and do this. So our function y of t is going to be equal to y sub 0 times e raised to the kt power. And in this problem, we know what y sub 0 is. So our initial mass is 100. We also know that the half-life of radium-226 is 1,590 years. So we know the amount at time t, which is 1,590. That should be half of our initial amount. So half of 100 is 50. And then we're going to go ahead and use this to solve for k. So we can divide both sides by 100. 50 divided by 100 is 1/2. And that's going to be equal to e raised to the 1590 times k power. And then we can solve for k by applying natural log to both sides. So we get the natural log of 1/2 equal to, when I take the natural log of the right-hand side, we get 1590 times k, which makes k equal to the natural log of 1/2 divided by 1590. Okay, and we have the same idea that we had in the previous example. At first glance, it doesn't look like k is negative, but because the argument of the log function is between 0 and 1, the natural log of 1/2 is a negative quantity. Okay, so that's an appropriate value for us for k. Okay, so if we're going to go back and do part A here, find a formula for the mass that remains after t years. Part A will be y of t equal to y sub 0, which is 100, times e raised to the natural log of 1/2 divided by 1590 times t power. Okay, so that is our exponential decay function in this case. Now, you want to leave that exponent k as an exact answer. You don't want to round that decimal, because if the numbers are big enough in the problem, if you round the decimal early, it's going to throw off the accuracy of your final calculation. Okay, so we're going to leave k exact, and then we'll go ahead and round it in our final step. Okay, part B asks us to find the mass after 1,000 years to the nearest milligram. Okay, so in part B, we are asked to find y, or the amount at time t is equal to 1,000. So this will be 100 times e raised to the natural log of 1/2 divided by 1590 times 1,000 power. And when we round that to the nearest milligram, that winds up becoming 65 milligrams. Again, you're rounding that value, so you have to use the approximately equal to symbol for part B. Okay, part C asks, when will the mass be reduced to 30 milligrams? Okay, so for part C, we're going to take our function here in part A. We want to solve for T when our amount is 30 milligrams. So we're going to plug 30 in for y of t, and then solve our equation for t. So that's equal to 100 times e raised to the power of the natural log of 1/2 divided by 1590 times t. Okay, so we're going to go ahead and solve for t. We're going to divide both sides by 100. So 30 divided by 100 is 3/10 equal to e to the natural log of 1/2 divided by 1590 times t power. Then we're going to go ahead and apply natural log to both sides. So that's going to give me the natural log of 3/10 equal to, when I take the natural log of the right-hand side, that just leaves me with the natural log of 1/2 divided by 1590 times t. And then I'm just going to multiply both sides by 1590 and divide by the natural log of 1/2. So we get 1590 times the natural log of 3/10 divided by the natural log of 1/2 is equal to t. And that makes t approximately 2761.775 years. Okay, so doing a half-life problem that is an application of, in this case, exponential decay. All right, let's move on to our next example. So next example says a city had a population of 10,000 in 1980 and 13,000 in 1990. Then it says, assuming an exponential growth rate, estimate the city's population in 2000. Okay, so this, once again, we have dy dt is equal to k times y. Here we have two initial conditions. Okay, so we know the initial population, y of 0, is 10,000. And then 10 years after that, the population is 13,000. So y of 10 is going to be equal to 13,000. Okay, and what this is asking us to find is the population in 2000, which is y of 20. So that's what we're solving for in this problem. Okay, so if we know we have a differential equation, dy dt is equal to ky, then that means that y of t is equal to y sub 0 times e raised to the kt power. Okay, so I'm going to use the first initial condition where y of 0 is equal to 10,000. I'm going to use that to solve for y naught. Okay, so y of 0, which is equal to 10,000, is equal to y sub 0 times e raised to the k times 0 power, which makes y naught equal to 10,000. Okay, so our function y of t is 10,000 times e raised to the kt power. And again, we know we are looking at exponential growth here because as time elapses, the population is getting larger and larger. Okay, we can take this second initial condition here and use it to figure out k's value. Okay, so we know that y of 10 is equal to 13,000, and that's equal to 10,000 times e raised to the k times 10 power. So we're going to use that equation to solve for k. So when I divide both sides by 10,000, we get 13 divided by 10. You want to write that as 1.3, that's fine, is equal to e raised to the 10k power. And then I'm going to solve for k by taking the natural log of both sides. So we get the natural log of 13 over 10 is equal to, when I take the natural log of the right-hand side, that gives me 10k, which makes k equal to the natural log of 13 over 10 divided by 10. Okay, so that makes our function then y of t equal to y naught, which is 10,000 times e raised to the natural log of 13 over 10 divided by 10 times t power. And then we are asked to calculate y of 20, the population in 2000. Okay, so y of 20 is 10,000 times e to the natural log of 13 over 10 divided by 10 times 2 power. And then when we calculate the population at that time, y of 20 becomes 16,900 people. All right, that is an exact answer, so we don't have to use the approximately equal to symbol for that. Okay, so last example here to wrap up the first part of 9-4. Okay, so this example says in 1970, the world population was approximately 3.5 billion. Since then, it has been growing at a rate proportional to the population, and the factor of proportionality has been 1.9% per year. At that rate, in how many years will there be 1 person per square foot of land? And we're told that the land area is approximately 5.5 times 10 raised to the 15th power square feet. Okay, so this one here, we're told the factor of proportionality is 1.9% per year, which means that dy dt is equal to, when we plug that percentage into our differential equation, we have to write the percentage as a decimal. So 1.9% as a decimal is 0.019 times y. Okay, so we're going to go ahead and solve that differential equation to generate our exponential growth function. Okay, so we're going to go ahead and solve this by integration by separation of variables. So we get 1 over y dy equal to 0.019 dt. And then we can go ahead and integrate both sides. So we get the natural log of the absolute value of y equal to 0.019 t plus c. Again, I'm going to apply e to both sides. So that gives me the absolute value of y. And then I'm going to go ahead and rewrite the right-hand side as e to the c power times e to the 0.019 times t power. And we're going to do just like we've done in the previous examples. I'm going to get rid of the absolute value bars on the left-hand side by putting a plus or minus in front of the right-hand side. And then I'm going to go ahead and rewrite plus or minus e raised to the c power as y sub 0. Okay, so we know that y of 0, the initial population in 1970 was 3.5 billion. So that is 3.5 times, I believe it's 10 to the 9th power. Okay, so we can go ahead and substitute that in for y naught. Okay, so y of t is y naught, which is 3.5 times 10 raised to the 9th power times e raised to the 0.019 times t power. Okay, so we want to figure out how many years it would take from 1970 for the population to be the same as the land area. Okay, so we're going to go ahead and plug 5.5 times 10 to the 15th power in for y of t. And that's going to be equal to 3.5 times 10 raised to the 9th power times e raised to the 0.019 t power. And then I'm going to go ahead and solve my equation for t. So I'm going to divide both sides by 3.5 times 10 to the 9th power. And that's going to give me the natural log of 1,571,428.57 is equal to e raised to the 0.019 times t power. Oops. Sorry, and then it should give me this, and then I'm going to go ahead and take the natural log of both sides. So when I take the natural log of the right-hand side, that just gives me 0.019t equal to the natural log of 1,571,428.57. And then to isolate t, I'm going to divide both sides by 0.019. And when I do so, that gives me t approximately to be 750.921 years. Okay, and again, like it's not the most realistic example because like exponential growth and decay are not the best models for population growth. We'll take a look at a better model for population growth in class on Friday of this week. Okay, so that will wrap up the first part of this lesson on exponential growth and decay and half-life, and then we'll save logistic growth for in class later this week. All right, have a great day, guys.